Well, scholars, now we're going to learn about vertical asymptotes. They're surprisingly connected to x-intercepts in weird ways. So why do graphs make asymptotes? That's kind of the question we have for us today, or for this video. But first, we need to go all the way back to fractions, and we need to start with some cookies. Let's say you've got 10 cookies, and you cut the cookies in half. How many half cookies do you have? Well, hey, look, here's one cookie. I've cut it into a half cookie. Hey, here's a half cookie. And here's a half cookie. How many half cookies do I have? Well, hey, I've got 2 half cookies. So that would be, together, 10 divided by 1/2. 10 cookies divided by half cookies is going to make 20 half cookies. Right? I mean, that seems kind of obvious, but also like, wait a minute. This is where this whole KFC thing comes from. This is why it actually works. Notice you don't need any like Colonel Sanders nonsense to actually understand this. So when we divide a number by a fraction, okay, we already did the 10 cookies. You got 10 cookies if you divide it into thirds. All right, well, I got 10 cookies divided by 1/3. Hey, that's going to be 30 1/3 cookies. I've got 10 cookies divided into fourths. Well, that's going to be 10 divided by 1/4 is going to be 40 cookies. If I take 10 cookies divided into 10th cookies, hey, that's going to be 100 cookies. Notice what's happening. The fraction and the denominator is flipping around and becoming multiplication again. Again, this is because dividing by a division, the inverses undo each other and it flips back around to multiplication. So it's like the reciprocal of a reciprocal becomes just a regular number. So now let's look at this in function form with the function f of x is 1/x. We're going to start at the x equals 10. So if I'm writing x as a fraction, I could think of it as 10/1. If I'm writing f as 1 over this, well, that's going to be 1 over 10/1. All right, and then rewriting that, that's just 1/10. So then evaluating that, hey, it's still like 1/10 or 0.1. If I do this with 1, it's like 1/1. And then I've got 1 over 1/1. And then it's still 1/1. Simplified, which is just 1. Now, when we actually get to the fractions, like this is a 1/10. So I'm going to have 1 divided by 1/10, which means rewriting with the cookies, it's actually 10, so the actual amount is 10. So this fraction, 1/100th, is really 1 over 100. So rewriting the function, so I'm going to input the 1 over 100 into my function. So I've got 1 over 100. And so that's going to flip back to be 100, the reciprocal over the reciprocal. So notice what's happening. It's getting larger each time. So if I do 1,000th, it's going to be 1 over 1,000th. And then that's going to become 1,000. All right, this is going to be 1 over 10,000. 1 over 10,000, which is going to become 10,000. So as we are, notice what's happening here. As my x is getting smaller and smaller and smaller, as it's getting closer and closer to 0, the number itself the output is increasing by quite a bit. And that's happening again because of the cookie thing. If I take a cookie, divide it into a smaller and smaller fraction of a cookie, I'm going to get more and more pieces of that. We can do this again for negatives. It's going to look exactly the same, except it's going to have a negative. And then when we graph it, it's going to look like this. So notice at 10, I had about 1/10. All right, at 1, it was at 1. 1 divided by 1 is 1. But then again, it starts going up. And the closer I get to 0, the farther up the function value is. However, when we go to the negative side, that flips around here. And then there's the question of what's happening right at 0. All right, what is happening at 0? Okay, well, nothing's happening. That's weird. Okay. Numerically, if you plug it in the calculator, you're going to get something that looks like error if you plug it into the table. And we get an error because we are dividing by 0. All right. I know, I think that's a cool picture. So, why can't we actually divide by 0? We need to think back to what division actually means. So again, we're going to do cookies. Let's say I've got 60 cookies, and I want to distribute my 60 cookies equally to my friends. And I want each friend to get 5 cookies. How many friends would get 5 cookies? Well, okay, I'm going to take my 60. I'm going to divide it by 5, and that's going to equal 12. Okay. Now, what if I've got same scenario, but I want each friend to get 10 cookies? Well, that would be 60. 60 divided by 10, which would be 6. So only 6 friends could get 10 cookies. All right. What if I wanted to do 3? Well, 60 divided by 3 would be 20. 20 friends could get 3 cookies. If I wanted to do 2, 60 divided by 2, that means 30 friends could get cookies. I'm starting to get really hungry for cookies. All right, so then 60, what if everybody wanted to get 1 cookie? If I wanted to, well, then I could have 60 friends. And then we can start then going into the fraction stuff with like, well, what if we wanted half cookies and yada yada. But what about dividing by 0? Now, take that same scenario, and instead, I've got 60 cookies. I want to distribute the cookies equally to my friends. I want each friend to get 0 cookies, no cookies. How many friends will get 0 cookies? So if you think about it, like I can actually snap my fingers right now, and so can you, and give everyone in the world, and in the universe really, 0 cookies. I just did it. You could try this at home. It still works. Okay? So that I'm not being a very good friend if I'm doing that, but notice that it doesn't quite make sense to give 0 cookies because nobody ends up with an actual portion, which is kind of why you can't really divide by 0. But what's actually happening is if you're dividing into 0 with cookies, 0 amounts of cookies, you're actually getting an infinite amount of things. I could literally give everyone in the universe 0 cookies with the snap of my fingers, and hey, I just did. And so can you. Isn't that magical? All right. But so what is actually happening when you're dividing by 0 is it becomes a positive or negative infinity. And so, which gets us to in calculus, 0 and infinity are basically reciprocals. I think we've talked about this before, but 1 over infinity is 0 and 1 over 0 is infinity. Now, there's actually quite a few arguments about this. That's not exactly mathematically correct. And in fact, during the first century of calculus, people fought about this. As in, bishops got involved, level of mathematical fights. Like the clergy got involved, which is absolutely hilariously fascinating. So if we're being actually mathematically accurate, you would say 1 over infinity is approximately equal to 0, and 1 over 0 is approximately equal to infinity. But these approximations are not just like rounding errors. They are as close as you can possibly get, which is why they're basically, you can get away with this for a very long time. Actually, I don't even think I realized this was wrong until I started teaching calculus. So what actually happens when we graph a division by 0? So let's look at this function. F of x is x squared minus x minus 6. Okay, we can break it into factors like we did with the zeros. Okay, and hey, look, notice that. Hey, look, there's an x-intercept right there. Whee! Here's another x-intercept here. Oh my gosh, great. So what happens when I graph this? So it'd be the function, 1 over x minus 3 and x plus 2. Well, what's happening at the same point as these zeros on this function, now that we've literally just taken this function and put it in the denominator? All right, what's happening here? Well, instead of a 0, instead of an x-intercept, that's where we get vertical asymptotes. So what happens? What creates? So what's the connection between zeros, x-intercepts, and the asymptotes of this? Well, the zeros of when it's in the numerator, all right, become, so here's the zeros, here's the x-intercepts, right? Become the vertical asymptotes when you put them in the denominator. So the same phenomenon, if it's in the numerator, is an x-intercept. If you put it in the denominator, it becomes an asymptote because dividing by 0 makes infinity. The reciprocal of 0 is infinity. So what creates vertical asymptotes? Dividing by 0. I misspelled 0. Notice that that's sort of parallel to what we talked about, what creates x-intercepts, and it was multiplying by 0. So again, notice the connections between these. We're learning this stuff at a higher level we probably have before. So the best way then to find vertical asymptotes algebraically is going to be, we just set the denominator of a function equal to 0 and solve. That's it. So let's do an example of one. We've got a function that has a numerator function, denominator function. Here's our numerator function. Here's our denominator function. So my first step is I'm just going to set the denominator to equal to 0. And then I can find the x-intercepts. I'm going to use the 0 product property, which allows me to split these up. Okay, because anything times 0 makes 0. And then I can solve these individually. And notice we're using the same skills as with the x-intercepts. And then these are the actual equations of the vertical asymptotes because they're x equations, they're vertical lines, so it's x equals positive 3 and x equals negative 4. One thing I do want to say is you have to write the full equation if IB or someone asks you for vertical asymptotes. Okay, you cannot just write that it equals plus 3 because it's not a point value. It is an equation of a line, a vertical line. That's the asymptote. Okay, so it's not, sometimes you can get away with it. You absolutely cannot get away with it here. No, here's another word. So we can apply this to trig. So notice, if you remember, the secant function is really 1 over cosine. Okay, so finding, I would want the decimal of the cosine values. When is cosine going to be equal 0? I'm going to sketch those vertical asymptotes, and then I'm going to use this to figure out what secant would be. So wherever there are zeros on cosine, there should be vertical asymptotes. So I want to show you what that looks like. So here's cosine. So hey, here's a 0. 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 And then, yeah, there's going to be vertical asymptotes on secant anytime cosine has a 0. If we go to the next slide, you'll see, hey, look, there it is. There's my vertical asymptotes, just where I said they would be. Right? So that's what the secant function looks like. It looks like this guy. So notice it's just the reciprocal of this. And we can do the exact same thing for sine. So here's an x-intercept, 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 x-intercept. Here's the vertical asymptote. There's where this one's going to be, where this one, this one, this one, this one. There it is. Hey, and there they are. Look at that. There are some vertical asymptotes, right where we thought they would be, right where sine is equal to 0. So if you know the shape of the sine function, you then basically know the shape of the cosecant function. If you know the shape of the cosine function, you basically know the shape of the secant function. So what about the intercepts of rational functions, the x-intercepts of rational functions? Well, if to find the vertical asymptote, we set the denominator equal to 0. To find the x-intercepts, we're just going to set the numerator equal to 0 and to solve, right? So notice this kind of builds on what we had before. And so we can think of these other functions, like when we just had f of x that had, no numerator 4. You could think of it, we had x squared minus 3x minus 10. We could think of that as over 1. So how would I find the x-intercepts? Well, I'm just going to set the numerator in this case, the implied numerator. Remember, we have this implied division by 1 always, all right, equal to 0. So this thing always kinds of works, even if there isn't a denominator to find x-intercepts. But then if we want to find vertical asymptotes, we set the denominator equal to 0, and then we solve. Let's do that on this one. So if I want to find the x-intercepts, I'm going to set the numerator equal to 0. So that's going to be x plus 5 equals 0. x equals -5. So over here at -5, there's going to be some sort of x-intercept. I'm going to do the same thing for my denominator. So I'm going to say x minus 3 equals 0, x plus 4 equals 0. Well, then that's going to be x equals 3 and x equals -4. So I'm going to have a vertical asymptote here at -4, and I'm going to have a vertical asymptote here at 3. Notice you're getting a sense of the shape of the graph, a sense, just from these, from the asymptotes and solving these. So here's what it actually looks like. And again, notice, hey, look, right there. There's my x-intercept. That was from the numerator when we set that equal to 0 and solved. And then here are my asymptotes. Here's this one. It was created by dividing by this one when this one equals 0 at -4. And then when this one equals 0 at 3, it makes this vertical asymptote. So we can do the same thing with tangent. So plot the x-intercepts. Remember, so this is what's the numerator is going to make my x-intercepts when that's 0. And then the denominator is going to make my vertical asymptotes. Right, so every time sine is 0, that's going to be here, it's going to be here, 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 here. And then I'm going to have vertical asymptotes whenever cosine is 0. That's going to be here, and here, 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 and here. And sure enough, when we look at the actual tangent function, hey, there it is, right there. Here's my x-intercepts, just where I said they would be. And here are my vertical asymptotes. So notice it's the same concept. Even though we're doing it with trig, it's the same idea. That when the function, when the numerator outputs a 0, you're getting an x-intercept, okay? And when the denominator is outputting a 0, you're getting a vertical asymptote on the graph, all right? So this is sort of a big chart that sort of summarizes all this stuff. There's this other thing called holes, which is in the middle, where you're actually both multiplying and dividing by 0 at the same time. That's when you've got a factor of, like, say you had an x minus 4 divided by x minus 4 on the as a factor term in the numerator and the denominator. So yeah, so again, the x-intercept, the graphical name is the x-intercept. What's going to equal 0? The numerator is going to equal 0. What operation with 0 is happening? It's kind of like we're multiplying by 0. What's it going to look like? You're going to have a factor on top and then something else, or just 1 on bottom. Numerically, it's going to look like 0 over like 4 or 5 or some other number. Okay? The math names that we have for this are zeros, roots, or even solutions to f of x equals 0. If you double that root, that's when it bounces against the x-axis. And then I've been using this iTunes card analogy that might or might not be helpful to you, because there are different kinds of 0, different kinds of nothing, that I think is hard to like encapsulate, and we've come up with different mathematical terms that mean slightly different things. So for instance, this sort of x-intercept kind of nothing means I have an iTunes card, but then I have exactly $0.00 on my iTunes card. Now the vertical asymptote, just to go through it, that's vertical asymptote. What equals 0? The denominator equals 0. What operation is happening with 0? We're dividing by 0. What does it look like? You're going to have some sort of stuff and then some sort of x minus c or 3x minus 4 or something like that. You're going to have variables in the denominator. Numerically, it's going to look like some sort of number over 0. The math name for this is either does not exist or undefined. Okay? Undefined, because you can't quite define infinity. Okay? The doubles, if you have a double, like if this thing ends up squared, what it looks like is it ends up, if you graph it, it looks kind of like this, where it goes up and then goes back down instead of switching like the normal version does, which looks like this. Okay, so it kind of bounces against infinity. That's how I think of it. Scholars in the past have found that to be truly baffling, and they really hate when I say that. So I don't know, I'm just letting you know. The equivalent sort of nothingness is I don't have an iTunes card, in a sense. So this is the difference. This kind of nothing is I have 0 on my iTunes card, and this is I don't have an iTunes card. Okay? So, a whole is when you're both multiplying and dividing by 0. Okay? It's also called a removable discontinuity. We're not going to deal with these much. I just want to let you know that they exist. So yeah, what equals 0? Both the numerator and the denominator are equal to 0. We're multiplying and dividing by 0. The factors would look like this algebraically. On the numbers, if you were like evaluating at that point, you'd get a 0 divided by 0. And the math name for that is not 0. It's not undefined. It's indeterminate. Okay? If you double it, nothing special happens. And this is kind of like, I don't know how much money is on my iTunes card, and I am not able to figure it out. Like I've lost the password to the account or something like that. And the reason why it's indeterminate is, let's go back to the zero product property. If I've, say, got 0 times A equals 0, well, then I solve for A, that would be 0 over 0. But because of the zero product property, A could literally be anything. So that this 0 over 0, because of the zero product property, A could be anything. I cannot determine what it is, so we call it indeterminate. Now, why this ultimately matters is wholes are where calculus happens. That's actually like basic calculus stuff, is we're going to be exploring wholes and such. That's where most of the time you don't encounter these except when you're trying to do calculus. So that's why that actually matters. So that's all I have for vertical asymptotes. Notice again, we're putting all these concepts together and seeing how they interconnect. It's really important that you understand what's distinct about each of them, but also the connections between them. Scholars generally struggle either with one or the other. They either think that they are completely different things with no connection to each other whatsoever, or it becomes like this big giant ball of mush where they're all the same thing. They're not the same things, but they are related things. Okay, they are all cousins and related to each other. So make sure you understand that.